we are looking at elastic collisions. So we have the idea of momentum. We know that momentum is mass times velocity. And we have, I wrote this equation down, which is on the equation sheet, which is what I call the elastic collision equation. So that's used for elastic collisions because it incorporates the idea of conservation of kinetic energy. So we kind of want to have that in mind as we use that. So when we do an elastic collision, we're going to use conservation of momentum and this elastic collision equation. So the problem I have here is a 3.5 kilogram block going to the right at 3.7 meters per second, a 6.2 kilogram block going to the left at 5.9 meters per second. They collide, they bounce off of each other. What are the final velocities? All right, so let's start with momentum. All right, so let's get into the habit of starting with a physical equation rather than just putting numbers in. It's very tempting just to start writing 3.5 times 3.6, just to start writing the equation, but we got to start with initial momentum equals final momentum. All right, so you have to write PI equals PF to begin it, and then I'm going to do this step here. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. M1 is 3.5 times 3.7 plus M2 is 6.2 times negative 5.9. Be careful, the negative sign, it is going to the left. Equals M1 is 3.5, V1 final we don't know, plus 6.2 times V2 final, which we don't know. 6.2. All right, so there's our equation, and there are the two unknowns, V1 final and V2 final. Now, the next equation is elastic, I'll just say elastic. So this equation is, you'd have to write down the equation first, because that's all there is. There is no statement or, that's the equation. So you got to write it down first, then put in the numbers. V1 initial is 3.7. V1 final we don't know. V2 initial is negative 5.9. And then V2 final we don't know. All right, so these are our two equations that we're going to use. We have this one and this one. So we're solving both of those simultaneously for V1 final, V2 final, V1 final, V2 final. So it's not really that bad. Let me take this one and solve for V1 final and plug it in there. You got to pick something. So basically solve one equation for one variable, plug it into the other equation, and then solve. So let's take this one just because it's shortest, but it doesn't really matter. So we get V1 final equals, so it's going to be V2 final, so minus 5.9 minus 3.7. So 5.9, 3.7, so minus 9.6. Minus 9.6. All right, so then I'm going to take that and plug it in to here. All right, so then this equation becomes, so let me just calculate that whole left side here. 3.5 times 3.7 minus 6.2 times 5.9 is negative 23.63. So negative 23.63 equals 3.5 times V1 final, which is all of this. V2 final minus 9.6. And then plus 6.2 times V2 final. All right, expand this out. Let's see, so negative 23.63 minus 3.5 V2, or equals, that's equals, okay. Negative 23.63 equals 3.5 V2 minus 3.5 times 9.6, 33.6 minus 33.6 plus 6.2 V2 final. All right, so then I'm going to collect the V2 finals together, move this over to the other side. So 33.6 minus 23.63 is, so that's going to be a 9.97 equals something times V2 final. So that'll be 9.7. So I'm combining these two V2 finals together, 3.5, 6.2, and that makes 9.7. So V2 final is, now before we get the answer, you want to think, what's V1 final? Here's 1, here's mass 1. I don't really label them so well, 1 and 2. After the collision, they're colliding together. 1 is going to go to the left and 2 is going to go to the right. So what relative velocities do we expect? It's not clear, which one's going to speed up or slow down. You could figure it out, but just, immediately without looking at the numbers, you wouldn't be able to tell. But we do know that number 1 is going to go to the left and number 2 is going to go to the right. So V2 final should be a positive number, which it turns out to be. So 9.97 divided by 9.7. So 1.03. 1.03 meters per second. And then now to get V1 final, we're going to plug it back into here. I don't know how to do this without making more of a mess here, but V1 final equals V2 final minus 9.6, which is 1.03 minus 9.6. So basically just minus 9.6 is negative 8.57. Let's see if I got the right answer. Yes, I did. Okay. So as expected, V1 final goes to the left. Now what happened was, this is a big mass with a big velocity. So what it did is it not only did it reverse the direction, both of them reverse direction, but so it sent mass 1 going to the left with a velocity much bigger than its original one. So it did a lot of, change for mass 1. Whereas mass 2 being bigger, it rebounded to the right, but with not much velocity. So most of you could say most of the momentum of this one kind of went into sending that one out much farther. Well, basically, momentum is conserved, but since this one is big and has a big velocity, the transfer a lot of it went to this one and sent that back with a big velocity. All right, so that's the concept there. Okay, next problem is going to involve two train cars colliding. All right, we're going to have a train car of 5,000 kilograms. Let's see, where is it? Moving to the right at 4.2 meters per second. So this is going to be a completely inelastic collision. So completely inelastic. Now, the problem doesn't have to say completely inelastic for you to know what to do. That's just the label for it. What the key is that the cars stick together. When you see that, then you know it's completely inelastic. But it's kind of fairly obvious. I mean, there's nothing really you have to process here. Basically, if the cars stick together, then they're both definitely moving at the same velocity. So it's not like you have to memorize any new formula. You just have to know that they're moving together, so their final velocity is some unknown velocity v. All right, so let's see what the problem is. What did I say? 5,000 kilograms. And the other one is 4,500. So it's moving at 4.2 meters per second. And now the first example we did the other day was this one was at rest, but this time I'm going to give it a velocity. Let's say it's moving at 1.5 meters per second. So it has to be moving slower than this car for there to be a collision. But they're moving in the same direction, but this one's going to catch up and then they're going to connect together. So you can kind of imagine what's going to happen and think. You're going to get a bigger velocity or smaller velocity for each one. And what you'd expect is this one is going to be a little less. So it's moving at 4.2 now. When it connects up with this one, the whole thing is going to be slower than 4.2. And similarly with this one, when this thing bumps into it, that's going to give it a boost, so it's going to be moving at more than 1.5. So basically we expect V to be somewhere between 1.5 and 4.2, somewhere in the middle. Okay, so being an inelastic, completely inelastic collision, we don't use the elastic collision equation. We just use momentum. So we start with Pi equals Pf, and then we write down the momentum for each one. M1 V1 initial plus M2 V2 initial equals, now here, since they're stuck together, it's the total mass, M1 plus M2, and some final velocity V. There's not two separate velocities. They're together, so it's one velocity. All right, numbers here. 5,000 times 4.2 plus M2 is 4,500 times 1.5 equals, so 5,000 plus 4,500 times big velocity V. So this is a much simpler problem. There's only one equation, and basically you just type it in and solve it. So 5,000 times 4.2 plus 4,500 times 1.5 equals, divided by 9,500, which is 2.92. Let's see if I got it right. 2.92, yes. So big V equals 2.92 meters per second. So that is in fact in between 1.5 and 4.2 as we'd expect, and basically with a completely inelastic collision we use Pi equals Pf, and that's pretty much it. Now just be careful, if you have an example where this one is moving to the left, you'd have to have a negative sign. So that could be, they could collide and stick together. And just if something's moving to the left, put a negative sign when you insert the number. And that's about it. A train car of mass 6,200 kilograms moves at 3.5 meters per second to the right. A second train car of mass 5,000 kilograms moves at 0.5 meters per second to the left. So that one's kind of like rolling slowly, where this one's actually kind of moving. They collide and stick together, find their final velocity. It would of course be easier to do just to draw the picture, but sometimes I'll ask a question in terms of words so that you have to figure out what it looks like. So there's the answer. This one, there's an elastic collision of these two blocks. We have a 1.5 kilogram block moving to the right at 3.4 meters per second. We have a 3.2 kilogram block moving to the left at 4.3 meters per second, and find their final velocities. The answers are V1 final, if that's 1, is negative 7.09 meters per second, and V2 final is this one going at 0.61 meters per second.